So what we're going to do, what my intention today is I want to look at how to plot a quadratic graph, but also how to sketch them. And sketching them is the thing that you would need to do from now, from year 12. Plotting you can just finish this year. And what needs to be done? In order to be able to produce very lovely graphs, we need, of course, a pencil. What we're going to do is we're going to plot the points that you did on the sheet before. So, on this first set of axes that I've got here, you'll see there's two equations on here. So what I'm going to do is I'm going to start with y equals x squared, and I'm going to plot away. Now, we're going to -3 is up here to 9. There it is. -2.5 is 6.25, so it's going to be about there. I just heard the immortal phrase, I have no idea what we're doing. So okay, so. Yeah, so if you go to the next page. Yeah. So these are coordinates. So that's the x coordinate, y coordinate, x coordinate, y coordinate. I am plotting these points. Yep. So, -2 to 4. -1.5 to 2.25, it's about schmeh. -1 to 1. Well, I say it's about yay, above 2. You'll have to estimate to the best of your ability.
The yay is varied.
Yeah. 2. Okay. 0.5, 1 to 1, 1.5 to 2.25, 2 is to 4, 2.5, 6.25, and 3 is to 9. This lovely type of graph has its name. It's a parabola. It is not a parabola. That's a hat that flies. It's a pun. So parabola is the name of the graph, and it is used often, especially used a lot in physics, as well in terms of motion. And one of the things that people who first start drawing parabolas do is they try to treat it as if it was a dot to dot. And make this very awful looking line sort of thing. A parabola is a smooth curve. So if that means, because you remember how with our dots, listening up, remember how sometimes when we try to do 2.25 it's like yay. What we try to do is when we draw the graph, we try to sort of get it so it's through most of those dots. So when you're drawing this particular graph, I better vary my voice to prevent the yawns. So we're just doing a one smooth curve looking like that, and a smooth curve going up like that.
Actually got curves though.
Real graphs have curves. Now, so similarly, what we want to do is we do the same for 2x squared. Okay, 10. Looking up here, listening, please. Looking up here, thank you. Thank you. Listening, thanks. As I've been going around, the thing that I really like, and you might be worried, it's a wee bit wobbly, or it's like, it may not be hitting all the points, that is perfectly fine. The one, as you can see from mine often, if I'm having to draw by doing a plot, it will kind of look like it's melted in the sun a bit. That is natural. When you get to circle graphs, even more so. But, listening please. Okay. So, the one thing that is I would like to be as essential for any graph drawing, if you go on to methods, if you go on to further maths, anything like that, is that all graphs should be one continuous line. Because sometimes what happens is that if you're like me, who likes to draw and do cartoons and things like that, when I would first do parabolas, listening up at the back especially, is that my temptation is to do like little sketches like that. And no, none of that. So what you'd want to do is you'd want to make it one continuous curve. Okay, so what I want to do here is also to demonstrate a couple of things, some properties of parabolas. What do you notice the difference between, put your hand up if you can tell me what would be the one thing that's difference between x squared and 2x squared in terms of the shape of the graph? What do you notice, Mr. Schwab?
One's a lot goes in and one's wider.
Yeah, so you'll find with that first graph here, which is up here, the number at the front of the x squared, what that does, it acts as a stretch. It stretches it out. It's what we call, now for those biologists in the room, you'll be familiar with pupils and things like that. When you close your eyes, your pupils dilate. Listening thanks? Pupils dilate, they get larger. That number at the front of the x squared dilates the graph. So, that is what we would refer to as a dilation factor. We say that it's been dilated by a factor of 2. So that's what we refer to here. The 2 at the front there is a dilation by a factor of 2. So, we can see if we look at the next graph down there, which is brackets x minus 2 squared, compare it, it's a similar shape to the y equals x squared. It's still that same sort of width. Put your hand up, you can tell me what's the one difference between y equals x squared and y equals brackets x minus 2 squared. What is the difference in terms of where the graph is? Here's Matt, where's Miles?
The bottom point isn't on 0.
Precisely, the bottom point isn't on 0. In other words, it's just that it's moved over to the right. It's the same graph as y equals x squared, it's just been shifted over. The little minus 2 is actually an instruction to move right
Minus 2 is
by 2. Yeah.
oh, mine done plus you.
And in maths, we always like to have different terminology. We can't say it's buggered on over to 2 on the right. It's actually been what's referred to as translated. Okay? So, given that terminology, I want to see if anyone's brave enough, put your hand up, if you could tell me how might you describe the third graph. What's happened in the third graph?
Moves less by 3.
Yeah, so we use the term for moving. What's our term for moving?
Translated less
Yeah.
by 3.
Yep.
Is that a translation factor?
Oh no, it's just a translation. So you don't need to write factor. So, the things I wanted to introduce today was the idea that a number at the front of x squared is a dilation factor. If you've got a little lovely brackets in there, and it says minus some number, that's translating to the right. And if it says plus some number, it's translated to the left. So, what we're going to look at now, as I was mentioning to some people there, plotting is very annoying. It's very painful, and from this point, what I want to emphasize is the skill of sketching. So, yes, sir, Mr. Schwab.
Is the reason it's written in brackets because so you can see at a glance whether it's translated or not?
You are spot on. Now, so the question is why, because normally you might remember with quadratics, we spent all of that time last topic expanding brackets. And what does it look like when you expand things? When you draw a graph, it's actually really handy to keep them in the brackets because it's a quick and easy way to tell us when I want to sketch a graph, if it's moved left or right. So, what we've got to do is we've got to start sketching. So, what I'm going to do is I'm going to move to the next page. So, I mentioned before that this was going to be slightly of an art class. What I want to do is I want to give you the opportunity on this next page to have a go at trying to sketch this picture as one continuous line. Do as many as you feel is necessary. This is not all we're doing. I'm going to show you how we do it on the axes as well. I would like you to practice as many times being able to comfortably sketch this parabola. There's an example of some very lovely sketches going on there. So that kind of shape is fantastic. Doesn't matter if it has a little bit of a wobble in there. Here's another lovely set of examples. That's a very lovely shape, getting that lovely curve, confident curve. Why is it important to be able to sketch the picture? So to be able to do this, it makes drawing the graph infinitely quicker. Thanks. So what I'm going to do here is I'm going to show how the graph looks like in each of these set of circumstances. So y equals x squared. So literally, if I want to draw that graph, all I need to do is that. That was our y equals x squared graph. And look, I better put in my intercepts because that's what I've been told to do since year 9, drawing linear equations. There's my intercepts. It hits the x and y axis at 0, 0. Now here's a thought. We haven't done this yet. It's got a little this next one on the right has a minus sign at the front. What do you think might happen to the graph? It would be upside down. Thank you, Mr. Musgrove. Okay, so this one at the bottom, it says x minus 1 brackets squared. Can anyone tell me, remember from their previous page, what has happened to that graph? Mr. Daniels?
Hang on.
Oh, Mr. Musgrove, can you help us out?
Translates to the left.
No, I'm afraid it's translated to the right. Well done. Ouch.
You just move it.
Yep. So, listening up, thanks. That point, which is what we call a minimum, because it's the lowest point, what would be the coordinates, Mr. Musgrove?
1 and then 0.
Yep.
It would be negative 1.
Well, no, it is 1, 0. It's moved to the right by 1.
Wait, what?
Yeah, so because we're moving to the right by 1, it's got the coordinates 1, 0.
Then what did it go?
So now I'm very happy that I've got a confused person because it says minus. Why is it moved to the right in positive direction if it's got a minus in there? We shall sort that out very shortly. Okay, and then we've got x plus 4 squared. Where is that being translated and by how much, Miss Mullins?
4 to the left.
It is 4 to the left.
Oh, thank you.
Yeah. Yeah. You'll also notice, listening up, thanks. You'll also notice that I haven't bothered putting a scale at the bottom. That just because it makes it much easier to draw without worrying about a scale. When you're sketching a graph, because the emphasis is on the word sketch rather than plot, you can actually invent your own scale. You'll notice that I've pretty much drawn the same graph, I've just moved it left or right. That is totally legit, perfectly fine. The only thing that's missing, there's one important set of coordinates that's missing from that bottom two. What's missing, Mr. Schwab? The y-intercept. Now, Mr. Spalding, can you possibly tell me, how do I find a y-intercept from any graph? With the equation? Yeah, what about the equation, Mr. Musgrove?
Substitute x for 0.
Yeah, substitute x for 0. So to find the y-intercept, I'm replacing, so y-intercept, you make x equal to 0. So I'm replacing x with 0. 0 minus 1, that'll become negative 1 squared, which is 1. So that is got a y-intercept of 1. What I'd like you to do is work out what the y-intercept of x plus 4 is. And I would like you to put your hand up and to show me if you think you've got that correct. So I want you to find the y-intercept of the graph on the right.
It's
Anyone else found the y-intercept? Want to show me? Fantastic, it is indeed 0.16. Okay.